Hello, Proof and TA. I'm Xiayin. We are Group 11, and our project is partial duplicate video retrieval with deep metric learning. Our presentation is divided into 4 parts: background, models, results, and conclusion. Now first comes the background. Now let me briefly explain the form of these videos we used. We can find that the edited video here contains clips made by other users. Those videos are composed of partial duplicated videos. Also, we can call them NDVs. Currently, video has become a popular information medium, taking Bilibili as an example of a typical platform. Its average monthly video submission volume currently reaches 8.4 million. Various video platforms contain a large number of edited videos. Therefore, the realization of partial NDV retrieval is very meaningful. It can help to protect the original, check video source, and optimize revenue sharing for video creation. The existing NDVR method is divided into video level, frame level, and hyper level matching. Check-bit copy detection task is a well-known work. The difference between this work and NDVR lies in the source of the video corpus. Another important area is metric learning. This is to learn a distance function to measure similar objects are close, dissimilar objects are far away. Deep metric learning currently mainly uses the network to extract embedding, and then use L2 distance to measure the distance in the embedding space. Next is the segmentation of long videos. First, a various of inputs can be defined for segmentation systems, such as foreground and background. Next is about feature extraction, including extracted from the entire image, such as color and histogram features. The other type is the area-based feature extraction technology. Finally, there is modeling and classification. There are generally the following methods: unsupervised method, SVN, random decision forest, Markov random field, conditional random field, and neural network. There are also some typical methods. For example, Oswald mainly treats each image in the video as an independent picture for processing without considering the timing information. Mask trick considers timing information and still treats each frame as a static image. The key method to realize video segmentation in the paper is to combine online and offline strategies.
Hi, I'm Du Yu. I will introduce the model part of our project. First, let's have a look at the pipeline. We will input a query video to the deep metric learning model, and the output is the embedding vector of each frame. Then we will use this embedding vector to calculate the continuity and do the similarity retrieval. First, let's have a look at the deep metric learning model. This is the pipeline of the deep metric learning process. First, we use a pre-trained CNN to do the feature extraction. Then the deep metric learning model will map the feature to an embedding space for the similarity calculation. Let's first get in depth for the feature extraction part. We use the VGG16 to do the feature extraction. We know that the filter from different layers will have a different receptive field. So if we combine the information from the feature map of different layers, we can get an image feature from low level to high level. So we use the function below to compress the feature maps of each layer into a vector. The length of the vector equals to the numbers of channels of the layer. Then we will concatenate this vector into a long vector. We call it feature descriptor. Now we get the image feature. To calculate the video feature, we will sum and normalize the feature of each frame, so the video feature has the same shape with the image feature. After getting the feature of each frame, we will talk about the feature embedding and the similarity calculation. The feature embedding process uses a simple DNN. Since the VGG16 already provides high-level features, the objective of this DNN is to map the feature into a embedding space, which minimizes the distance between the embedding of the near-duplicate video and maximize the embedding of non-NDV. The distance calculation uses the squared Euclidean distance, and the similarity calculation uses this function. We can find that if the distance between the two videos is small, the similarity is high. So the near duplicate video should have a high similarity. And for the training process, we use the triplet loss function. Let me explain the loss function. The input of our model is a triplet, which is made up of three video, one query video, one near duplicate video with the query video, and one non-NDV. And we calculate the distance between the query video and the near duplicate video and the query video with the non-NDV. And if the distance between the two NDV plus the gamma, which is a margin, is still smaller than the distance between the non-NDV, the penalty will not be applied to the loss function. And if this distance between the NDV is very large, the loss will also be very large.
Hello, I'm Bincheng, and I will introduce our overview of the model's pipeline. I will introduce the partial duplicate video retrieval part in details. After the DML models, we can know the feature of every frame of our query videos. Then we describe a new model called Video Frame Retrieval Memory Model to make a better result. In the query frames, there are three conditions for two nearby frames. Condition 1, two frames come from the same videos and they are continuous frames from the database videos. Condition 2, the two frames are not continuous, but they are still in the same video. The condition 3 is two frames from different videos and of course, not continuous. In order to make a better result, we notice that two continuous frames are a very possible condition. But there are some conditions, like condition 2 and condition 3, where when the author of the query videos cut the videos and the two frames are not continuous. Despite the feature likelihood, the video frame itself can be regarded as a Markov chain model. We can build a time sequence model, referring to some popular models like LSTM RNN. We can memorize the previous information of the time series. So this is our final result of VFRM. You can see the structure. It contains a gate part and two layers to calculate the similarity. If the gate algorithm comes out that the frames from T and T plus 1 are continuous, the gate will open and the memory of previous frames will be passed through and finally affect the final similarity result of next time. But there's a question, how to calculate whether the frames from T and T plus 1 are continuous? So we design a segment DNN model to tell us whether the gate should pass through the memorized information or not. The segment DNN model will catch the feature information of the frames of T and T plus 1, and then it will tell us whether the two frames are continuous or not. So how we train the DNN model? We just randomly pick up the frames from same videos or different videos, and then we train the DNN models. Finally, we can let it tell us whether the two frames are continuous or not.
I'm Peng Zifan, the first member of the group. I'm going to introduce a part of evaluation and results.
The first thing I'm going to illustrate is dataset. We have three datasets for training and the testing. The first is training dataset. We leverage CSIT web video dataset, which is deployed for training the deep metric learning model. The dataset is originally stored on server at CTU, collected from YouTube, Google Video, and Yahoo Video. The second is evaluation dataset, or called test dataset. The test dataset is generated automatically for specific requirements. We retrieve some original video from Bilibili video site. And the third is segmentation, DNN, training dataset. We generated this dataset automatically for fitting the DNN, which contains 18,000 positive samples and 18,000 negative samples. Each of them contains 2 frames and a label to market whether the 2-frame transit. Next, I'm going to introduce the form metrics, which are widely accepted. The first is accuracy, and it calculates all the samples that are recognized correctly and represents the proportion of correct prediction among the total number. And where TP is the true positive and TN is the true negative, and FP is false positive, FN is the false negative. And second is precision. Here is the formula, denotes the proportion of true samples among all positive samples. And third is represent the proportion of all video transitions are correctly classified as transition, which is called recall rate. And the fourth is mean average precision, MAP, which uses the area under the PR curve as a measure. Evaluates the average AP value for multiple individuals in validation set, and the QR denotes the validation set. This slide shows the results of our model. Left figure shows accuracy and training loss with different number of layers in DML. We noticed that the loss decreased faster and smoothly, which is very reasonable because the input of a DML model is already high dimension features extracted by VGG16 and the DML. Red figure is the PR graph of DML model and the baseline. We can find that the feature embedding process significantly improves the classification precision on hard sample in the data set. The next slide shows the precision recall graph and accuracy of segmentation model, which has a good performance. We can say these are the similarities of 3 typical videos. The first is pure cut video with few edits. We can see we retrieve the video correctly and clearly. And the second is video with clips not in DV. We can see some similarity has some blank. It's very low similarity. And the third is the video with a lot of noise. And all the clips that have corresponding exit video in the database are retrieved correctly. Here are 2 figures with a more intuitive feel. Shows the segmentation of similarities, which are simple video staging and video with plenty of noises. The first is the simple video example. We can see we have 4 video clips and 3 segmentation, and is shown here, is marked by this triangle here, and it's very clear. And the next is a video with plenty of noises. The below graph is a similarity graph. We can see it occurs some blank. This blank may be the complex, the noise, the reason. And the next part I'm going to introduce is conclusion and future work. To summarize, we presented a new model for partial duplicate video travel, which leverages the effectiveness of existing deep metric learning. And also we introduced CNN and fully connected layers. Our architecture is based on LSTM and networking network. In the future, we want to explore more precise and accurate video feature embedding method. And in current DML methods, it compresses the whole video frame into one single embedding. And we want to introduce a slide window to improve it. Next, we will introduce and compare these 2 methods. In addition, we will increase the similarity compression in some video frames with noises and find some method to calculate the similarity more accurately and improve the model's robustness. Thanks for listening. Thank you.